Okay, folks, this is the third installment in this section. This is just a quick review. If you want to look on this board, you can freeze things right now and zoom in on that, take a look. That's a summary of what we've discussed so far. And we are going to do example 3 found on page 417. We're going to do the entire thing again. So if you just finished watching the other one or tuning into this one, we're going to do the entire example again. So it says, find the exact value of the expression with a calculator. Oh, without a calculator, sorry. Find the exact value of the expression without a calculator. So if you're going to do it right, we're not allowed to use these tools. And when they say exact value, they mean if it's irrational, put a pi or a radical in it as appropriate. Because those are irrational things. So exact value. So the first one is the inverse cosine of negative root 2 over 2. Now try to remember this from what we learned yesterday, that when you're doing inverse anything, you've got to reverse the question in your mind. The question in your mind when you see this has to be, what angle do I know of whose cosine is negative root 2 over 2? And by the way, you're only allowed to look in first and second quadrant for it. Do you understand the restrictions and how to view this? Since it is a negative thing that we're looking for, that means we're restricted to only second quadrant. So what we got to do, if you want a picture of it, and I always like to draw a picture because I'm very geometrically oriented. I realize this has got to be in second quadrant. I need to draw an angle whose cosine is root 2 over 2. And if you understand, if you've done this enough, you understand that's a 45-degree reference angle. Right? But what I'm really after is this angle. That's 3 pi fourths. So the answer to this is 3 pi fourths. You okay with that? Did you see how that all happened and all the decisions that had to be made? As soon as you see this, you say, oh, good, I'm only allowed to look in 2 quadrants. What is it for cosine? And you think, it's first and second. Then you look at this and say, oh, it's got to be second, because that's where cosine's values are negative. So then you think, then you look at this and you say, that looks familiar. What angle does that belong to? If it were in the first quadrant, it would belong to pi fourths. So that's your reference angle in the second quadrant. Then you reconcile it by having this angle start from 0 and come around it. There, 3 pi fourths fits into this range of values. The reason you don't report it as pi fourths is because that would be something in the first quadrant, which would also be acceptable, but this wouldn't be negative. See what I mean? It's got to be 3 pi fourths. It's got to get you into the second quadrant so it can be negative. Okay, that's the A part. B part says the inverse tangent of root 3. Okay, first thing, it's an inverse, which means it's restricted to 2 quadrants. You think, okay, tangent inverse, restricted to 2 quadrants. Got to be first and fourth. Okay, and then you look at the value of what you're inverse tangenting, and it's positive, which means you'll be looking for the angle in the first quadrant, because that's where they're positive. And then you got to think to yourself, okay, root 3. This is, I tried to teach you this, and maybe you haven't had enough experience with it, but this is what goes through my mind. Hopefully it will yours eventually. When root 3 is involved, tangent's either got to be a lay down 30, 60, 90 or a stand up 30, 60, 90. The only 2 possibilities are root 3 or root 3 over 3. Root 3 divided by 3 is way smaller than root 3. We're talking about the big one. So we choose the bigger angle, pi thirds. This is a stand up triangle, 30, 60, 90, because the tangent has got to be this leg over this one, which means the value of it's got to be greater than 1. Root 3 is greater than 1, 1.7 something. So the angle would be pi thirds. That is the answer to this. And pi thirds fits into this range of values for tangent. It fits between negative pi halves and pi halves. So it's the correct value. You see what I'm saying? Everybody clear on why we chose pi thirds and not pi 6? Because I can talk more about it if you want. Okay. The third one is the rough one. This was going to take a little more talk. Please either give me a funny look on your face like that, or raise your hand or something if what I'm saying doesn't make sense to you. Okay, so this one's it's a double one. We're inverse cosining a cosine. So we have the inverse cosine of the cosine of negative 1.1. Okay, now you've been taught order of operations says get inside the parentheses first and do what you can in there first. It's interesting because the instructions say that we have to give exact values, and yet this is not a familiar angle. And this is an angle because we're cosigning it, not inverse cosigning it. This is actually an angle. This is negative 1.1 radians. It's slightly more than 60 degrees, but it's negative. And since it's negative, we will open it down. So if we're looking at just this part, forget this part for a minute, just look at this part. To understand that, what we're going to do is we're going to start, because this is in the forward direction, cosine regular. We're going to start here and we're going to open that angle. That's 1.1, negative 1.1 radians. Since it's negative, we open it this way, and the terminal side ends up being right there. Do you understand that? Okay, now here's the hard part. This is something you have to remember from what we've discussed so far. If I were to draw this, I'm going to erase this because I'm going to have to draw through it. If I were to draw the triangle up that goes with this, and remember that we're going to make this a 1 on purpose, then this angle, which is negative 1.1 radians, that's an angle. It just hasn't got a pi on it, so that's a little awkward. But if this is a 1, then the cosine of that angle is this length right here. Okay, so if you understand that this blue line right here is the value of this right here. This is blue. Right there, it's that length. So what we're asking now is, what angle do I know of? Because now we're inversing, we have to reverse our thinking. What angle do I know of whose cosine is this in the first or second quadrant? Not negative. Because if I open up an angle, from here in the first or second quadrant that has this exact value for its cosine, it means I have to open up this angle in that quadrant so that its cosine will be this when I drop it down. And what angle is that? It's 1.1. So the entire value of this is 1.1 radians because that's the angle in the first or second quadrant that has the same cosine as this angle.
So why isn't it in the second quadrant?
Because if it were in the second quadrant, this blue line would be over here and it would be negative. It wouldn't be the same as this line here. Cosine's got to be this line. And the triangle that I can draw that has a cosine this long can be drawn in this quadrant or this one, but it's not going to be this one because that would shift the blue line over and it was not the same thing. It has to be exactly that line, that distance right there. And that has to go to this triangle in the first quadrant, whose angle is 1.1 radians. So that's the ultimate answer.
Okay.
Do you want me to go through it again faster and with less talk?
Can you just cancel out the cosine?
No. And the reason why you can't cancel out the cosines is because this angle that we're looking at is not in the region of stuff we're allowed to look at. It's not in between here and here. If it were, we could. But it's not. It's elsewhere. It's one of the other quadrants that this is not defined in. So we got to do a little more thinking. So we open up this angle, this inside the parentheses. We open up that angle, which is open downward. We draw a triangle to go with it. Then you have to recognize that if this is 1, which it always should be, then this length right here is the cosine. That is the value of this. Whatever that blue line's length is the cosine. So what we want to do now is find an angle, because this says find me an angle in the first or second quadrant whose cosine is this, whose cosine is blue. And it's got to be first quadrant with the same size angle, but it's got to be positive because we opened it upward into the first quadrant. See it? Kind of crazy, I know. It's wild. Okay. Now look at look at example 4 for a minute. We're switching gears here a little bit to talk about the inverse tangent. I'm on page 418. For those of you watching this in the middle, it says example 4, describing end behavior. So now we're going back to the graph that we saw yesterday of the inverse tangent, which is the one branch that goes through the origin. You see the pictures there. And it says describe the end behavior of the function inverse tangent x. Means as x gets way, 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 way far to the right, what's y becoming? Isn't it? For the inverse tangent function, which is the second picture, if you let x go way, 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 way up to the right, what are the y values becoming? Pi halves. If you let them go way, 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 way left, it's becoming negative pi halves. And so remember, we express things like this when we talk about end behavior. The limit as x goes way to the right. We call that infinity. The y values end up at pi halves. That's what they're approaching. We don't say that it actually arrives. We say it's getting closer to this. That's what this whole thing means. And the limit as x approaches negative infinity, the y values are going down that far. They're trapped in between, but they never touch it. So we say that this is a bounded function, and yet it has no max or min. Bounded means it's got a floor and a ceiling, but it never touches each. It just hovers in between. You know what I'm saying? Yeah, a little bit? Okay. So there's no max or min here, but it's definitely a function. All right. Now we're going to compose trigs and inverse trigs, much like we did with that cosine and inverse cosine, only they're not going to be the same ones. We might do the sine of an angle and do the inverse tangent of it. Don't panic. Right at the very top of page 419 is what you keep wanting to do, Brooke. That's okay. That's good that you want to do it, but you got to understand there's only under certain circumstances. I have an asterisk by both of these statements at the top of page 419. You may do it as well if you like. It says, the following, well, it says down at the very bottom of the previous page, it says, the following equations are always true whenever they are defined. If you have the sine, by the way, sine is defined for all real numbers. Sine is. If you have the sine of an inverse sine, the big one, the sine, which has all real numbers for its domain, can undo the little restricted guy and always give you x. Always. If the sine, cosine, or tangent without the inverse on it are on the outside. We haven't seen that because, see, that's different from this. We have the inverse cosine on the outside here. That's different from what you're looking at in that first line. Would be reversed. We said the cosine of the inverse cosine, then they can undo each other every time because you got the big one attacking the little one, basically. And that can be undone. But if you've got it in reverse, which is the second line, inverse sine of a sine, inverse cosine of a cosine, inverse tangent of a tangent, you got to look really, really hard when you finally do the inverse part of it and make sure you're in one of the quadrants where it's defined. You got to be careful with that. Don't just undo each
Without any if it's in the correct range.
other. They will undo each other, as the second line says there, if the angle on the big angle on the inside is in one of the quadrants prescribed by the inverse quadrant on the outside. But if it's not, you got some thinking to do. Okay. Okay, example 5. Composing trig functions. It says, compose each of the 6 basic trig functions with inverse sine of x and reduce the composite function to an algebraic expression involving no trig functions. What? That's crazy. Those are those instructions. But here's how we do it. It says, compose each of the 6 basic trig functions. So, well, it says, with inverse sine of x. So we have to, we're focused on inverse sine. So if inverse, what we have here is the inverse sine of x. Means that this says, find me an angle. That's what it says. Find me an angle whose sine is x. There you go. I found it. You see what I did there? Because the sine of this angle is whatever this is, x, the opposite side over 1. That is x. The inverse sine of x is theta according to the picture that I drew. It's the angle whose sine is x. Now, it could be anything. I drew in the first quadrant to avoid problems. You don't have to draw, you don't have to draw it in any quadrant. You just got to angle such that when you take its sine, gives you x. I did. Now it says define all the 6 trig functions based on this. Well, we need Pythagoras' help. We need something for this. This would be, if I call this, I don't know, a for just a minute, then Pythagorean theorem says that a squared plus x squared equals 1. And so a squared is equal to 1 minus x squared. And so a is equal to the square root of 1 minus x squared. Most people at your level can do that in their head. If you can't, then write it down. It's Pythagorean theorem that's going to provide us with this length right here. But it needs to be in terms of x. Okay? The reason it needs to be in terms of x instead of a or something like that is because it says, compose each of the 6 trig functions and reduce the composite function to an algebraic expression involving no trig functions. It doesn't say it has to involve that, but it does. You're going to have to trust me on that. All of these sides have to be written in terms of x or constants. So now that we have that, if you understand how we did that, because if you really understand this conceptually, it's saying, find me an angle whose sine is x. There it is. Now find the 6 trig functions of that angle. Well, we needed this side in order to do it. So Pythagoras handed us that. So now we finish the problem, which is to say the, let me start one out this way. The cosine of theta is going to be this over 1, right? Which means that the inverse cosine of this is theta.
Please say that again.
Do you understand this?
Kind of.
Cosine of that theta is adjacent over hypotenuse, and adjacent over hypotenuse is just adjacent because hypotenuse is 1.
Okay.
That means if I were to solve that thing for theta, write an expression for theta, it would look like this. Theta is equal to the inverse cosine of 1 minus x squared. I'm sorry, square root of. Because I got inverse cosine both sides to get theta by itself. So let me see if I'm really following the instructions. Compose each function and reduce the composite function to an algebraic expression. Let's see what they want. Oh, we're going to compose each function. Let's go through it. Oh, I see what they're doing. We're going to compose each function with this. You know what a composition of function means? You're going to take something and stuff it into something else. That's composition, right? So I didn't have this quite right. Though the concept is correct, I didn't have it quite right. I didn't fully understand what they want me to do. They want you to do this. They want you to compose the cosine of the inverse sine of theta. I'm sorry, of x. Don't panic. Brooke, you're already looking worried. Don't look worried yet. Hang on, give me a second. Do you remember? This is a composition of the cosine with the inverse sine, which is what they told us to start with. Okay? But what is this? This is theta. Isn't it? So what they're really asking you to do in a really obscure, scary way is to find the cosine of that angle, which is the square root of 1 minus x squared. They want you to find the tangent of the inverse sine of x, which means the tangent of theta, which would be x over the square root of 1 minus x squared. You following? It's not as bad as it looks. The inverse sine of x is theta. So you're tangenting theta based on this triangle. Once Pythagoras gave you all 3 sides, you just read it. So now what would the secant of the inverse sine of x be? I don't need those parentheses. What would that be? It would be this thing's reciprocal, because it's secant. It's a secant of the same angle. Or you can say this has got to be adjacent over hypotenuse, so secant is hypotenuse over adjacent. That's a couple ways you can look at it, right? What's the cosecant?
No, that's secant.
What's the cosecant of the inverse sine of x? 1 over x. Because the sine was x. So the cosecant of that angle is 1 over x. And what would be the cotangent?
Square root of 1 minus x squared.
Reciprocal of tangent, yep. The main thing they're trying to drive home into your mind is that this should not be that scary. Even though you've got a tangent of the inverse sine, all that kind of, just remember, please try to remember that these things, those are angles. So find the cosine of that angle. After Pythagoras hands you the other piece of it, then you can just read it straight off of there. Do you understand what I'm saying?
What if it was, instead of sine, opposite of side in there, it was opposite like tangent or opposite of cosine inside the parentheses?
Then they will give you this information at first, and they will say the inverse. They might say the inverse cosine of x. Find me an angle whose inverse cosine is x. Then you would put x here, and the square root of 1 minus x squared here,
Okay.
and then read it from there. They said tangent is x, then you would put x here and 1 here. and find this from Pythagoras. This isn't always going to be 1, but it is in this case. But if they said tangent is x, the inverse tangent is x, you would put x here and 1 here and let Pythagoras tell you what this is as a radical and then read them.
Okay.
You see what I mean?
Yeah.
Okay. Okay, last thing, and this is actually kind of interesting and rather powerful. It's kind of a fun thing. So I'm going to erase this so we can put it on the board. There's only one thing left. Yep, we're still running. That's good. Yesterday I looked up there and the screen was black and I went, all right. All right, so here's our situation. This is it's a story problem. It's kind of cool. It says the bottom of the 20-foot replay screen at Dodger Stadium is 45 feet above the playing field. As you move away from the wall, the angle formed by the screen at your eye changes. There is a distance from the wall at which the angle is the greatest. If you can get that angle to be the greatest, you get the least amount of distortion entering your eye from the size of the screen. It's huge. But if you're standing right underneath it, you don't see very much. You don't see very much of what's really going on. A lot of distortion. If you back up, you see more and more and more. As you back up past the sweet spot, you back up more and more and more. It's got a little bit slightly less comprehensibility, I guess, because the angle between the bottom and the top gets smaller as you back down. As you go forward, it gets a little bit bigger, but as you get to closer and closer and closer to the screen, that angle gets so big that you got such distortion you can't see it. There's an optimum place to stand, is what they're saying. Okay.
We can use this when we have our own houses and we're trying to install our TVs.
Yes, absolutely. What you'll want to do when you're installing your own TV, especially if you hang it on a wall, is to tip it forward a bit. You don't want to leave it flat. So that the main thing is to try to get your line of sight to hit the middle and have the same angle going up to both. Yeah, you can use this. Your home theater to make it as perfect as possible. Okay, here's what it says. So let me read it again. The bottom of a 20-foot replay is 45 feet above the ground. Let's see, bottom of a 20-foot.
Yeah.
Oh, the screen's 20 feet tall.
Okay. That's
The bottom of the screen is 45 feet above the playing field. See the diagram on the left?
Yeah.
Okay. All right. As you move away from the wall, the angle formed by the screen at your eye changes. There is a distance from the wall at which the angle is the greatest. That's what we want to find. When the angle is the greatest. We're talking about theta, which is the angle between the blue and the blue. That's what we're looking for. It says there is a distance. Okay. What is that distance? So we're looking for x out from the wall where it's hanging. We're looking for how far back we got to stand so that theta is as big as possible. This makes sense to you? I'm going to draw the diagram up here so I can point to it. So we've got ground out here. Here's the wall that TV is hanging on, that big display screen. Here's the display screen. It goes from about here to here. So this right here, we're looking at it from the side. You'll understand that, right? Okay. We're looking at it from the side, and we're saying this is the optimum position. So we've got an angle here, and we've got an angle coming down here. And this is the theta that we wish to maximize, basically, by walking out this distance, making this be as big as possible. The thing that we assume is that the thing is on a wall, which is perpendicular to the ground. That's a good assumption. And that the ground is flat as you come out, which would be true of a playing field. And so we've got to try to figure out what that is, knowing that this piece right here is 45 feet, and this piece right here is 20 feet. That's about the only numbers that we get. And see if this makes sense to you. This is theta 1. This is theta 2, the entire thing. And the theta that we seek is equal to theta 2 minus theta 1. That makes good sense, I think, right? So now what we got to do is figure out what theta 1 and theta 2 is. And apparently, since there are nothing on the hypotenuses at all, apparently this whole thing is about tangent. Because we know something about the opposite thing. We know something about the ground we want to come out to, even though we don't know the value of it. That's what we're looking for. That's involved in the problem. And so let's start writing some facts that we know about these triangles. We'll come back to this idea. This is the big idea. We'll come back to that in a minute.
It's opposite over hypotenuse, so we could say it's 65 over x.
So what are you saying? The tangent of what?
Tangent of theta 2.
Okay, you want to do theta 2 first. That's fine.
Yeah, is
Tangent of theta 2 is?
65 over x.
Exactly. Okay. What's the other one? Tangent of theta 1 would be 45 over x. Is that right? Well, I need thetas. Oh, that's not that hard. Theta 2 is equal to the inverse tangent of 65 over x. Yeah. Theta 1 is equal to the inverse tangent of 45 over x. So that means when I come down here to solve this thing, it's going to be tangent, inverse tangent. Now, should we be in a degree mode or radian mode? Or does it matter? I'm just asking.
Probably in degrees, because you're looking at something for degrees.
Something
not
practical
for-
where people understand degrees better.
Yeah.
Yeah, degrees is fine. But now I want you to think about this, because we can't do this by hand anymore. These are not familiar things to look at. We're gonna have to grab our calculator. When I say what mode to be in, it's the indicator that we're gonna use our calculator. Don't grab it yet. Don't grab it yet. Think with me for a minute. When you do this and you calculate this right here, put it in your y1, what values of x do you suppose are reasonable? Because you're gonna have to set up a window where you can see this.
No greater than 90.
And you're thinking theta. I'm talking about x.
Yeah, well, that's looking, it has to be somewhere close to like 45 degrees. I'd say something around.
So we're not gonna go from 0 to 10. But we're also not gonna go from 0 to 1,000.
No, we're going to like 100.
So, yeah, so be reasonable about the footage and stuff that you see here. Maybe 100 might be good. We'll go from 0 to 100 since we're walking out from the wall. Think about this also with me. This is where yours comes in, Brooke. The y value, this is the y value that's going to kick out, which is this angle right here, and we're in degrees. What's reasonable for the value of y? It looks pretty tiny right here to me, but it can't get any bigger than 90, can it? As a matter of fact, I don't think it can get any bigger than about 20 or 30. But I'm going to let mine go from 0 to 45 and see if I get it from there. Because I don't think it's going to get any bigger than 45. That's just a guess. But you got to think about what these things represent and what reasonable sizes you have. So I'm going to build my window first. I'm going to let x's go from 0 to 100 by 10s. And I'm going to let my y's go from 0 to 45 by 5s, I guess. And I'm going to go to my mode and change things to degrees before I begin to calculate. And then I'm going to go to my y equals screen and type in what I wish to maximize here. So I have the inverse tangent. In the window that you chose, do you see a maximum?
Yes.
It's pretty subtle, but it's there. Do you see it? Those of you looking, this is what my window produced for me, and it's not great, but there is definitely a maximum there. It's very subtle, but you can see it on your screen. Go find it.
Okay.
What did you get for an x value?
54.08, whatever.
54 feet, basically. Because if you're actually going to do this, you're not going to worry about the 0.08. You're going to go out 54 feet, and that will give you a theta of only 10 degrees. But that is the maximum for viewing at 54 feet back. Looking up at it will give you your best undistorted view. It'll still be distorted some because you're on the ground. But that's the least distortion you'll get. Is that okay with that? Do you understand what I'm saying?
I can't figure out the graph. Like, mine's not graph.
Oh,
Did you switch your mode?
Yeah.
David, you have fun back there.
So much fun.
okay. It's because your one's in the wrong place. Why are we subtracting 1?
It's.
Okay, yeah, the inverse tangent is not the reciprocal tangent.
Oh,
The inverse tangent is the inverse tangent. So figure that out and retype. Okay. Using inverse tangent. Okay, for those of you viewing it, that's all you get. You can see the graph of this. Maybe on your calculators, there's a similar graph, although it's a little bit better. On top of page 421, you can see the maximum a little better, but we still found it, so there you go. Good luck.